Hello everyone. Today I'll discuss about the theory and application of microwave spectroscopy. As we all know that microwave is a definite kind of electromagnetic radiation. Thus it contains the same property of electric and magnetic wave as I have discussed earlier in my previous video. Before we start, we need to know some basic criteria of microwave radiation. Its frequency range varies from 300 MHz to 300 GHz and wavelength range is 1 mm to 100 cm. This microwave radiation is important in molecular spectroscopy as the separation between the quantized rotational energy level of molecules are the order of 100 joule per mole, which is the energy related to microwave radiation. Thus, the energy required for the molecular rotation of a molecule with permanent dipole moment is interactable with microwave radiation. So, rotational spectroscopy is also known as microwave spectroscopy. The necessity of the presence of permanent dipole moment can be explained by the separation of the electric charges which is responsible for the interaction with electromagnetic radiation. As rotation of permanent dipole moment active molecule is related to microwave spectroscopy, we need to know the nature of different kind of rotation related to molecule. In a three-dimensional space, molecular rotation can be segregated into three rotational components about three mutually perpendicular directions through the center of gravity, which are known as principal axis of rotation. Thus, a body has three principal moments of inertia. IA, which is nothing but rotation along bond axis, IB, which occurred due to the end-over-end rotation in the plane of paper, and IC, which is end-over-end rotation perpendicular to the plane of paper. According to the relative values of their principal moments of inertia, molecules can be classified into different groups. And to discuss the rotational spectroscopy of any molecule, we need to know the classification of molecule according to their moments of inertia. It can be divided into four categories of molecule: linear molecule, symmetric top, spherical top, and asymmetric top. In linear molecule, if we rotate it around three axes, it is evident that IB and IC are same and IA is very small. That's why we consider IA approximately equals to 0. Example is HCl. In symmetric top molecule, IB equals to IC but IA not equals to 0. Thus, two subclasses are generated. For one, IB equals to IC, which is greater than IA, which is known as prolet symmetric top, and another one, IB equals to IC but less than IA, known as oblate symmetric top. In this class, which is known as spherical top, where all three moments of inertia are identical. That means IA equals to IB equals to IC, which is known as spherical top molecule. As no dipole moment is possible in this case, that symmetric top molecule don't show any rotational spectroscopy, as we know that presence of dipole moment is important for showing rotational spectroscopy. The next class is asymmetric top, in which IA not equals to IB not equals to IC. It is known as asymmetric top molecule. Now, to deal with the rotational spectroscopy of any molecule, we need to know the energy required for the transition within the rotational energy level, which is quantized. By solving Schrödinger equation of a particular molecular system, we can determine the energy of rotational energy level. Here, I am starting this discussion with the simplest case of rotational spectroscopy, where molecule is a diatomic rigid rotor, which means that the bond length between two atoms remain constant during the rotation of the molecule. So, the Schrödinger equation for rigid diatomic molecule for rotational energy level is Ej equals to h square by 8 pi square I into j plus 1 joules. In this expression, h is Planck's constant, j is rotational quantum number which varies from 0 to upward, and I is moment of inertia, either IB or IC, because we know for linear molecule IB equals to IC and IA is approximately 0. So, how this moment of inertia or I is related to bond length of molecule, I'll discuss here. As in case of a rigid rotor molecule, bond length is fixed. We can show that M1 and M2 mass bearing two atoms A and B are joined by a rigid bond whose bond length is R0. Then R0 equals to R1 plus R2, where R1 and R2 is distance between the center of gravity and A and B atom respectively. As molecule rotates along center of gravity, thus M1R1 equals to M2R2. Thus moment of inertia about C, which is the center of gravity, is I equals to M1R1 square plus M2R2 square. Now we know M1R1 equals to M2R2. So by replacing the value here, we are going to get I equals to R1 into R2 into M1 plus M2. So combining the equations R0 equals to R1 plus R2 and I equals to R1 into R2 into M1 plus M2, we are going to get I equals to M1 into M2 by M1 plus M2 into R0 square, which is nothing but I equals to mu into R0 square, where mu is known as reduced mass. Thus, from rotational energy of molecule from Schrödinger wave equation, one can determine the bond length if we consider that the molecule is a rigid rotor. As spectral energy is usually discussed by the wave number, the Schrödinger equation can be represented as epsilon j. Epsilon j is nothing but Ej by hc, which converts the unit into centimeter inverse or represented the energy with respect to wave number. So if we just transform this in a shorter version, we are going to get epsilon j equals to b into j plus 1, where b is rotational constant, which is nothing but h by 8 pi square I into c, where c is the speed of light, h is Planck's constant as we have discussed earlier, and j varies from 0, 1, 2, as j is an integral number and it can increase from 0 to upward. From this equation, we can show allowed rotational energy levels of diatomic rigid rotor molecule. So, if j equals to 0, epsilon j equals to 0, thus the molecule is not rotating at all. For j equals to 1, epsilon j equals to 1 equals to 2b, and rotating molecule has its lowest angular momentum. So, with increasing j value, the epsilon j value increases in this manner. Theoretically, there is no limit to the value of j, but practically at a certain point, centrifugal force of a rapidly rotor diatomic molecule is greater than the strength of a bond and the molecule is disrupted. But at normal temperature, this point is not reached. Now we are certain about the individual rotational energy level, so we can discuss the corresponding rotational spectrum. Let's say the molecule is present at j equals to 0 or ground rotational state. Thus energy need to absorb to rise it to the next energy level, that is j equals to 1, is 2b. Then to the next one, from j equals to 1 to j equals to 2, the amount of energy required is 4b. In general, to raise the molecule from j equals to n to j equals to n plus 1 state, we need nu bar, or in the wave number, if we express the equation, that will be 2b into j plus 1 centimeter inverse. For rotational energy level transition, except del j equals to plus minus 1, all other transitions are forbidden. Thus, the selection rule for the rotational spectroscopy is del j equals to plus minus 1. Now we will discuss about the nature of intensities of the spectral line. There are many factors involving in the intensity of spectral line. First one is selection rule. Transition of molecule should follow selection rule. So for rotational spectra, when del j equals to plus minus 1, we will see spectra as the transition is allowed. But whether the transition from j equals to 0 to 1 and j equals to 1 to 2 is going to give us the same intensity spectra? The answer is no. We are not going to get a same intensity spectra when the transition of the molecule varies from its ground state and next excited state. So the intensity of spectral line depends on the population of the level. The first governing factor of the population of the level is the Boltzmann distribution factor, which is Nj by N0 equals to e to the power minus Ej by Kt. Thus, rapid decrease in Nj by N0 is observed with increasing J value and with larger B value or rotational constant value. That means that on increasing the J value, the population will be decreasing. So if the population is decreasing, the intensity of the spectral line will be less. And the second deriving factor for the population is the possibility of degeneracy in the energy state. In general, each energy level, for the rotational energy level I am talking, so each energy level is 2j plus 1 fold degenerate. That means the population is proportional to, depends on both the degeneracy factor as well as the Boltzmann distribution factor. So it is represented as population is proportional to 2j plus 1 into e to the power minus Ej by Kt. If we just differentiate this equation, we are going to get the maximum population at the nearest J value, and which is J equals to root over of Kt by 2hCb minus half. So from this curve we can show that how with increasing J value and as well as the degeneracy of the energy level, it shows that in this case here where the B value is 5 centimeter inverse, the population density is highest for approximately 2-3, this range, mostly 3 rotational energy level. The population energy, the population density will be more, and it will vary when the value of B changes. As we know that rotational constant or B is inversely proportional to moment of inertia, which is nothing but mu r square, thus we can say that rotational spectroscopy can vary with the change in isotopic substitution in the molecule, as the reduced mass changes on substitution and not the bond length. So we need to consider when we are doing any isotopic substitution, actually the bond length remains fixed and the mass of the system varies. So the reduced mass changes. Here a comparison between carbon monoxide, which is in one case it is 12 carbon and another one is 13 carbon. We are going to compare the rotational spectroscopy of both the substance, and we are going to see a variation observed in the rotational spectroscopy. Thus, observing the rotational spectra of any molecule, we can get an idea about the isotopic substitution as well. Up to this, I have discussed about rigid rotor molecule where the bond length between the two atoms is fixed. Now I'll discuss about non-rigid rotor, simply where bond length can change while rotation. Thus, concept of elasticity in bond arrived, which tells us that more quickly a diatomic molecule rotates, greater is the centrifugal force tending to move the atoms apart with respect to the bond length. So centrifugal distortion is now part of energy equation of non-rigid diatomic molecule. The equation is Ej equals to h square by 8 pi square I into j plus 1 minus h to the power 4 by 32 pi to the power 4 I square r square k into j square into j plus 1 whole square into j, which if we express the term with respect to epsilon j, we are going to get bj into j plus 1 minus dj square into j plus 1 whole square. So where d is the centrifugal distortion constant. Thus, while comparing the rigid and non-rigid rotor, we observe that the energy difference between the energy levels remain almost same at the lower J value. On increasing the J value, the amount of D, centrifugal distortion constant, become significant with respect to the equation, and which actually decrease the energy difference when the J value is higher, at the higher side. Till now our discussion is going with respect to diatomic molecule. Now we will discuss about polyatomic molecules. So first one is linear molecule. In linear case, basically the concept of diatomic molecule is a bit modified with respect to a polyatomic molecule when we are discussing the rotational spectroscopy. Definitely the presence of permanent dipole moment is necessity for showing rotational spectroscopy, whether it is a diatomic molecule or a polyatomic molecule. And as the number of atom in a molecule increases, thus the B value is smaller for polyatomic molecule with respect to diatomic molecule. So for a triatomic linear molecule, with respect to, if we just use the concept of the diatomic rigid rotor molecule, we can determine the bond length using the same concept. It can be determined. The next one is symmetric top molecule, where we know that IB equals to IC and IA not equals to 0. Thus, two rotational constants are available in this equation. One is J with respect to IB or IC. One is K with respect to IA. So, the equation is a bit modified here, and which is epsilon Jk, as two rotational constants are present there, is equals to b into j plus 1 plus a minus b into k square. So where b is carrying the same value, and a is nothing but presence of ia with respect to the equation b. So for all cases where k is greater than 0, rotational energy levels are doubly degenerate. Okay, and the selection rule is same, del j equals to plus minus 1, but del k equals to 0. Thus, two condition arises in this case for symmetric top molecule. In one case, k equals to 0, that means no axial rotation is possible, and another one is k is greater than 0, where rotation is possible along the symmetry axis. Thus, energy levels arrived for symmetric top molecule can be determined with respect to two rotational constant, which is J and K. Next one is asymmetric top. As we know that in asymmetric top molecule, IA is not equals to IB and not equals to IC, which is not equals to 0. Thus, there is no general term for determining the energy value for the asymmetric top molecule. We have to use the idea of linear and symmetric top molecule, and using these two concepts along with the symmetry of the molecule, we can get the energy of the molecule for each rotational energy levels in a asymmetric top molecule. So to know more about the symmetry of an element, you can check for the video, which is the description is given here. So now we are going to discuss about the instrumentation part of microwave spectrophotometer. Here is the schematic representation of microwave spectrophotometer. So we can see that first of all we need a monochromatic source to produce the particular frequency range, that is microwave radiation, and usually the source is klystron. So microwave radiation is produced from klystron, and after production it is guided by a waveguide, which is nothing but hollow rectangular copper or silver tube. So after passing through this tube, it is going to interact with the sample. So it is directed to the sample chamber, where as we know that rotational spectroscopy is related with the rotation of molecule or rotational energy level of molecule. That's why we are taking the sample in the gaseous state. So the vapor pressure of the sample need to be very less. It should be 0.01 millimeter Hg vapor pressure. So after interacting with the sample, it will change the energy levels and all, and we are going to get a spectra, which is nothing but the rotational spectra. So to get that spectra, we need a detector, which is nothing but a simple crystal detector. So after passing through the modulator, it is going to the detector. We are going to get a rotational spectra, and to check the rotational spectra we need a recorder to record the spectra, and after detector it goes to recorder, which is nothing but an oscilloscope, and we are going to get a recorded rotational spectra of a particular sample which is present in the gaseous state. Now we are going to discuss the Stark effect on microwave spectra. So Stark effect is nothing but the effect of electric field either placed perpendicular or parallel to the direction of radiation beam across the sample. As a molecule with permanent dipole moment is eligible for rotational spectra, thus effect of electric field can perturb the spectra, and due to Stark effect a shift in spectra is observed. So for linear molecule we are going to see the shift with respect to mu into E square, and for symmetric top the shift is proportional to mu into E. In this way, accurately, the dipole moment of any molecule can be determined without considering any interaction with respect to the intermolecular interaction or solvent effect using the Stark effect. So another importance of the Stark effect is the splitting of degeneracy of J values. As we know, for any J value, 2J plus 1 levels are observed because the J values are degenerated, which is otherwise not observed without splitting by the electric field interaction. Along with that, Stark effect can improve the signal to noise ratio by ignoring stray radiation, which is a great instrumentation improvement in microwave spectroscopy. For the application of a microwave spectra, there are n number of applications for particularly with this simplest form of spectroscopy. So now we are going to discuss some of those applications here. So though the microwave spectrum of a substance is very rich in lines, as we know that many rotation levels are populated at room temperature, but since those lines are quite sharp, their positions can be measured with great accuracy, and the identification of the molecule is possible with respect to the accurate measurement. So considering this, we are going to identify simple stable molecule in interstellar space, which is really fascinating. We know the amount of vapor pressure required for the sampling is very less in case of microwave spectroscopy. Thus, for liquid and solid also, it can be analyzed where the vapor pressure is low. So we can analyze those sample as well with respect to a rotational spectroscopy or microwave spectroscopy, but preferably the sample should be in its gaseous form. So in this way, many almost 130 molecules in interstellar space can be identified with respect to this microwave spectroscopy. Among some other applications, the determination of intermolecular sorry, among some other application, the determination of intramolecular hydrogen bonding is very important for determining the molecular structure and other conformers. Then the dynamic polymerization process is important to determine the presence of trimer or multimer, which can be explained with respect to microwave spectra is discussed here. Though it is not a part of microwave spectroscopy, but as we know that microwave radiation is involved in cooking and heating of food in microwave oven, I want to discuss a brief about it. As we know, only molecules with permanent dipole moment can interact with microwave radiation. So water has a permanent dipole moment, and water can interact with it. As water or OH group is abundantly present in food, it can easily interact with microwave radiation, but as the rotation is restricted within the food, so it cannot rotate as much as possible. That's why it will produce heat, and the amount of heat released due to this restricted rotation is used for the cooking purpose. In this way, in microwave oven, food is cooked. So in a nutshell, in this video, we have discussed about the basic theory and application of microwave spectroscopy. So if you have any other query, you can leave it in the comment section and I'll get back to you. And after watching this PPT, go by the book and you are going to get a better idea about microwave spectroscopy. Hopefully this PPT will help you understanding the basic concept, and we are going to discuss more about the other kinds of spectroscopy in my next video. So keep watching. Till then, bye.